Good afternoon.
Afternoon.
How you doing today?
Pretty good. How are you?
Pretty good. So today we're going to work on the Alka Seltzer Lab internalization, lesson internalization. And so with that, the objective was students will be able to conduct an experiment to investigate the rate of reaction to and then data extrapolation for multiple tables. And so with the know and show, thank you for doing the pre-work for that. And so thinking about the pre-work for the know and show, what do you think the impact of it is?
I think it's always good to review experimental design with the students, reinforcing knowing the difference between the independent variable, the dependent variable, and controls and constants. It will help them immensely on the ACT. A lot of that is very experimental design heavy. And two, as we work into the AP for All curriculum, one of the biggest parts of that, and one of the biggest points they can earn on that test is an experimental design question.
And so when you think about the rate of reaction specifically with what they need to know and show, and breaking down what they need to know for the rate of reaction and what they need to show, for you to break it down without the students and look over it again, what is the impact?
For the impact of surface area on rate of reaction, they need to know that when you have a larger surface area, there are fewer molecules interacting in the reaction versus when there's more surface area, there's more interaction. And then with temperature, they need to understand kinetic theory, that as you increase temperature, you increase the movement of molecules, and therefore that will increase the reaction rate.
So I definitely heard you. And so, like, thinking about the impact, like impactful meaning like you doing breaking down the know and show, actually able to say, hey, the kids will need to know this and show this, whether it is the surface area and the molecules or evaluating the temperature in the experiment. And so now we're going to go down to the just going through our alignment check. And so with the objective in mind and the criteria for success, in your own words, what is the big idea of this lesson that you want to explain to students?
This lesson is built into the unit that is on bonding, and I think a lot of times students don't realize that chemical reactions and bonding is occurring in everyday activities that they see all the time. So I really want them to get to thinking and observing chemistry as an everyday observable activity. It doesn't have to be fancy unknown chemicals, and that they have a direct effect on chemical reactions that occur within their bodies. You know, activities they do at home are chemical reactions.
Okay. And so I heard you say direct effect on chemical reactions and then the bonding that occurs. And so with the direct effect with chemical reaction and the bonding occurs, then you have the rate of reaction, right? And so with those in mind, I'm going to give you 2 minutes, and you can edit on your internalization if you want to, or you can put it in your notes. So in the next 3 minutes, I'm going to give you 3 minutes. I want you to make sure you explain the big idea that students should be getting from this lesson, how this lesson is connected to the instructional cycle, and if there are any, what gaps can interfere with the students mastering the objective. Okay. So go ahead and read back to me what you're going to take 3 minutes to do.
The big idea the connection to the instructional cycle, and the gaps to mastery.
Yes. Okay. Is 3 minutes enough?
Yeah, I think
Okay.
so.
Go ahead. I'm gonna put 3 minutes on the timer. I'll be working this way.
Yep.
As you're sharing out, I'm gonna check off what I have that's similar to yours, and then if I have anything or need to add anything, I'll just add it. Okay?
Okay.
Okay. Go ahead.
For the big idea, I want students to take away that chemical reactions happen in everyday normal events. This is modeled after digestion. Scientists can alter the reaction rate by changing surface area or temperature of the reactants. And this is a directly observable connection. For, you want me going? All right. The connection to the instructional cycle, we're talking about bonding a lot in this cycle, and so this lab, they get to observe bonds being really broken in this lab, and that there are physical observations that are evidence of bonds being broken, and so and I want them to relate it back to electron activity that we are doing kind of the end of this unit, going into the next unit. So everything has to go back to what are the electrons doing. And then gaps to mastery, if they They should have covered some kinetic molecular theory in middle school, but they probably have not talked about it since then, unless they've had physics first. So that might be something I have to reinforce. Getting products and reactants confused is something I see a lot. Understanding the difference between direct relationships and indirect relationships when they collect their data in their lab. And going back to experimental design, there's still always some students that are confusing independent and dependent variable, and then they get constant and control confused.
Yes. So I was going ahead and taking notes as well. So definitely when you think about the big idea knowing that the reactants are converted into products, right? And so we can alter that in a way. It is what we increase if there's a concentration increase or decrease, and that gives us that reaction. And then also too, going back to how is this related to the content or instructional calendar. It is because we talked about electrons last week, right? So we know that something is happening to these electrons, and we have to figure out what is happening, because then it gives us a reaction or another chemical. And then also to the bonding, the observing of the bonding, actually physically seeing what is happening with the Alka Seltzer tablet and how it's changing based on the solution or concentration that it's in.
Right.
I didn't go as far as back to the kinetic theory of them having that gap, but I was just thinking about currently recent, the gaps that will kind of maybe hinder mastery would be them understanding what is that constant, what's held constant in the experiment, because this is going into experimental design, and so knowing that our independent and dependent, I, the scientist, am changing something in the experiment, I, the scientist, is now observing or collecting this data, and them differentiating between the two, then goes back to the constant. So what is staying the same consistently, and then that goes with the extrapolation from multiple charts to see what indirect and direct relationships they have. So those are what I had as well.
Okay.
Do you have any questions about that? Okay. And so knowing that and then going into it, and so for us to make sure students are going to get to mastery in this lesson, thinking about the final product of the lesson, which is the lab and their data. And so when we look at the exemplar and we know the criteria for success, let's go ahead and state what students should be showing us with the experimental design and their final product for their lab write-up. So if we think about the criteria for success, what should students be able to show us on the paper that is exemplary, that will lead them to mastery?
On the handout, they're getting 2 tables, one for testing surface area and one for testing temperature. I want them for each table to identify the IVDV, the constants, and then I'm going to have them make graphs. It's not part of the handout right now, but
So can we pause for a second?
yeah.
So when we think about the criteria for success, right? When we think about those 3 to 5 things that students should be able to show within that problem or that lab, what should they be able to show us that we know that they have mastered identifying the rate of change and extrapolation from multiple data tables?
Okay, so what they need to be able to note is that the time it took for the whole tablet to dissolve was longer than the time it took for the little pieces to dissolve, and relate that to surface area. And then they need to be able to note that the time it took for the tablet to dissolve in warm water was faster than the time it took for the tablet to dissolve in the cold water. And then they need to be able, I think, I want to give them for either a post lab or an exit ticket, another scenario, a lab scenario.
So let's just stick with that one.
Okay.
Okay? Because we don't want to jump ahead, right?
All right.
So you were on to a very good start. So
Okay.
you want them to be able to, they should be able to show that the time, right,
Mhm.
of the tablets and how it's dissolving, whether the smaller piece or the larger piece is dissolving
Right,
faster
okay.
or slower, right?
Mm-hmm.
And they should be able to identify with surface area, right? Because that's going into them being able to show the rate of change,
Mhm.
right?
Right.
And that's a calculation, right?
Right.
And so when you go into the rate of change and get to push a little bit, because definitely on to a good start, but the calculations that are needed for rate of change.
Okay. We would have to do that, we would have to alter the setup of the
Mhm.
data tables a little bit, and they would have to do multiple trials.
Mm-hmm.
So that they could they could get more data
Mhm.
to calculate a more accurate rate of change.
Mm-hmm. And then that's actually pushing the bar for them, right?
Okay.
So I would keep showing that. So you want them to follow the protocol of the lab, and you want them to determine the rate of change for multiple variables, right? But you also too want them to be able to have that data table set, or be able to create the data table, but still knowing the equation for rate of change. Okay. So go ahead and jot that down.
Okay.
Do you have any questions about that, or is it clear?
That's clear, yeah.
Just to kind of like, you want to push that bar for them.
Right, yeah.
Because we know that they're able to pull information off a data table, right? That's simple.
Yeah.
You know, that's IOD, 301.
Mhm.
It's simple, pulling the data from a simple data set, but just to push that bar and have them, hey, we have multiple tables with multiple information, multiple sets of data. So how are we going to do it? And then if we need to, are we able to check our work with that equation?
Okay.
Okay. Other questions? Or you got any?
I have an unrelated question.
Mm-hmm. Okay.
Yeah.
So now we know that, and we're going to push that bar for them.
Okay.
So now going to misconceptions, right?
Okay.
And so we kind of touched on the misconception early on when you were talking about those gaps,
Mhm.
right? So let's go back and thinking about the gap, right? Or gaps that you named. What do you anticipate the biggest challenge being with the students with this lab?
I think for them, the biggest challenge is going to be two different things.
Mhm.
The relationship itself, knowing it being indirect
Mhm.
or direct,
Mhm.
and the molecular movements behind
Mhm.
why that relationship is that way
Yep.
is going to be an issue.
Mhm.
I think they will get the variables, the independent and dependent variable fairly easy,
Mhm.
but I think going back to what constants and controls are.
Mhm.
Because we have constants in this lab, but we don't have a control set up.
Mhm.
So I probably either need to set one up just to have,
Mhm.
to talk about real quick.
So I think if you, and you can do a brief constant, like in this room, right? The temperature is constantly, what, we can say is 68 degrees, right? But something is changing in the room. So I'm the scientist, I'm changing where you are sitting, but I'm keeping what the same. So if I change where you're sitting, you may get different results. But what did I keep the same? The temperature.
Right.
And that's something just quickly to go over, just to give them an intro about, or a review about. But going into mentioning an indirect and direct relationship, and that's what I was most concerned